NENOMATICA, where mathematics meets YouTube excellence. Example: 3 numbers form a geometric progression. There's some equals a, where a is positive. What are the minimum and maximum possible values of the product of the 3 numbers? We model the 3 terms by choosing the middle term as x and the common ratio as q. Then the terms are x over q, x, and qx. There's some equals a. From the picture, we read the equation x over q plus x plus qx equals a, multiply by q to remove the fraction. We get x plus xq plus q squared, x equals aq. Move all terms to one side. For real common ratio q, the quadratic in q must have real roots. So the discriminant is at least 0. b squared minus 4ac greater than or equal to 0. Here a equals x, b equals x minus a, and c equals x. Expand and simplify. We get x squared minus 2ax plus a squared minus 4x squared greater than or equal to 0. That simplifies to negative 3x squared minus 2ax plus a squared greater than or equal to 0. Multiply by negative 1 to flip the sign of the inequality. So 3x squared plus 2ax minus a squared is less than or equal to 0. Solve the boundary equation. 3x squared plus 2ax minus a squared equals 0. Using the quadratic formula gives x equals negative a and x equals a over 3. Therefore, x lies between negative a and a over 3 inclusive. Recall the 3 terms are x over q, x, and qx. Using the bounds on x, we obtain corresponding bounds for the other 2. Negative a over q is less than or equal to x over q is less than or equal to a over 3q, and negative aq is less than or equal to qx is less than or equal to aq over 3. Multiply the 3 inequalities side by side. The middle becomes x cubed, the left becomes negative a cubed, and the right becomes a cubed over 27. Finally, the product of the 3 terms equals x cubed. Therefore, the minimum possible product is negative a cubed, achieved at x equals negative a, and the maximum possible product is a cubed over 27, achieved at x equals a over 3. In this lesson, we will form a new quadratic equation whose roots are the sums of roots from 2 given quadratics. Specifically, if the first quadratic has roots x1 and x2, and the second has roots x1 prime and x2 prime, we will build an equation whose roots are x1 plus x1 prime and x2 plus x2 prime. Let the first quadratic be a x squared plus bx plus c equals 0, with roots x1 and x2. Let the second quadratic be a prime x squared plus b prime x plus c prime equals 0, with roots x1 prime and x2 prime. We will denote delta as b squared minus 4ac, and delta prime as b prime squared minus 4 a prime c prime. Define new roots capital X1 and capital X2 by capital X1 equals X1 plus X1 prime, and capital X2 equals X2 plus X2 prime. The quadratic we want has these as its 2 roots. First compute the sum S, which is capital X1 plus capital X2. This equals X1 plus X2 plus X1 prime plus X2 prime. By Vieta, x1 plus x2 equals negative b over a, and x1 prime plus x2 prime equals negative b prime over a prime. Therefore, s equals negative b over a minus b prime over a prime, which simplifies to negative of a prime b plus ab prime over a prime. Next, compute the product p, which is capital X1 times capital X2. Expand to get x1 x2 plus x1 x2 prime plus x1 prime x2 plus x1 prime x2 prime. Using Vieta, x1 x2 equals c over a, and x1 prime x2 prime equals c prime over a prime. The middle cross terms require the quadratic formula. Let x1 be negative b plus square root delta over 2a, x2 be negative b minus square root delta over 2a, and similarly for the primed roots. Then the sum of the cross terms simplifies nicely to be b prime minus the square root of delta times delta prime, all over 2a prime. Putting everything together gives p equals c over a plus c prime over a prime plus bb prime minus square root of delta delta prime, all divided by 2a prime. The desired quadratic with roots capital X1 and capital X2 is t squared minus st plus p equals 0. Substitute the expressions for s and p we just found. Notice that minus s becomes plus a prime b plus ab prime over a prime. To get clean integer, like coefficients, multiply through by 2 prime. Example, we will form a new quadratic equation whose roots x prime and x double prime satisfy two power sum relations. The given system is the sum of cubes equals 9 and the sum of squares equals 5. Step 1. Define S as the sum. S equals x prime plus x double prime, and P is the product, P equals x prime times x double prime. Step 2. Use standard identities for two numbers A and B. The sum of squares equals the square of the sum minus 2 times the product. The sum of cubes equals the cube of the sum minus 3 times the product times the sum. Substituting S and P gives us the following system in S and P. Step 3. From the second equation, isolate P in terms of S. P equals S squared minus 5 over 2. Step 4. Substitute this into the first relation. S cubed minus 3 times P times S equals 9. Then simplify carefully. Simplify carefully. Step 5. Factor the cubic S cubed minus 15 S plus 18 equals 0 by grouping. Recognize it can be written as S cubed minus 9 S minus 6 S plus 18. Grouping gives S times S squared minus 9 minus 6 times S minus 3, which factors as S minus 3 times S squared plus 3 S minus 6 equals 0. Step 6. By the zero product property, either S minus 3 equals 0 or S squared plus 3 S minus 6 equals 0. Therefore, S equals 3, or S equals negative 3 plus or minus the square root of 33, all over 2. Step 7. For S equals 3. Compute P using P equals S squared minus 5 over 2. That gives P equals 2. The quadratic with sum S and product P is T squared minus ST plus P equals 0. So T squared minus 3T plus 2 equals 0. Step 8. For S equal to negative 3 plus or minus the square root of 33 over 2. P is S squared minus 5 over 2. The corresponding quadratic family is X squared minus SX plus P equals 0. Final result. There are three possible sums S, each producing a quadratic with those roots. One clean explicit equation is x squared minus 3x plus 2 equals 0. The other two are obtained by substituting S equals negative 3 plus or minus the square root of 33 over 2 into x squared minus SX plus P equals 0. Example. We will form a new quadratic equation whose roots are the reciprocals of the roots of 4x squared minus 5x minus 5 equals 0. We will show two methods and confirm they match. Method 1. Use substitution. Let y equal 1 over x. Then x equals 1 over y. Substitute into the original equation, clear denominators, and simplify. Method 2. Use symmetric sums of roots. 4x squared plus bx plus c equals 0 with roots alpha and beta. Alpha plus beta equals negative b over a, and alpha beta equals c over a. The new roots are 1 over alpha and 1 over beta. Their sum is negative b over c, and their product is a over c. Then form the new equation x squared minus sx plus p equals 0. Conclusion. Both methods produce the same new quadratic. 5x squared plus 5x minus 4 equals 0. As a quick consistency check, the new sum of roots is negative 1, and the product is negative 4/5, exactly what we used. In this example, we will determine the values of a and b from two related quadratic equations whose roots are reciprocals. We will use a clean coefficient comparison argument. Example. The unknowns a and b appear in the first quadratic. The second quadratic is given explicitly. We are told that the first quadratic has roots that are the reciprocals of the roots of a scaled version of the second quadratic. Let us write the two equations clearly. Key fact: if ax squared plus bx plus c equals 0 has roots alpha and beta, then cx squared plus bx plus a equals 0 has roots 1 over alpha and 1 over beta. Up to an overall non-zero scale factor, the coefficients are reversed while the middle coefficient is preserved. To use this fact, we first align the middle coefficient. The first equation has minus 6x. The second has plus 3x. Multiply the second equation by negative 2 to make the x coefficient also minus 6. Now, compare the templates. For reciprocal roots, we reverse the outer coefficients and keep the middle one. The scaled second equation has coefficients -4, -6, and +2. Reversing the outer ones gives 2, -6, -4. Because our first quadratic already has the same middle coefficient -6, the overall scale factor must be 1. Therefore, a plus b equals 2, and b equals -4. Solving the little system gives it equals 6, and b equals -4. Quick check. Substitute the values a equals 6, and b equals -4 into the first quadratic. It becomes 2x squared minus 6x minus 4 equals 0. This exactly matches the reversed coefficient pattern of the scaled second equation, confirming that the roots are reciprocals as required. Takeaway: for quadratics with reciprocal roots, reverse the outer coefficients and keep the middle one. Matching the middle coefficient locks the overall scale, letting you read off the unknowns directly. In this example, we solve for the parameters m and k from two related quadratic equations. The roots of the first equation are exactly 1/2 of the roots of the second equation. Here is the precise statement. The roots of equation 1, x squared minus mx plus m minus 4 equals 0, are half of the roots of equation 2, x squared minus parenthesis k, plus 2 close parenthesis times x minus k equals 0. Method 1. Because every root of the first equation is half of a root of the second equation, let y denote a root of equation 1, and set x equal to 2y to land on a root of equation 2. We substitute x equals 2y into equation 2 and simplify. Now compare this new y equation with equation 1, y squared minus m, y plus m minus 4 equals 0. Matching the coefficients gives two simple equations that determine m and k. Solve the system. From the first equation, 2m equals k plus 2. Substitute k equals 2m minus 2 into the second equation. m minus 4 equals -1/4 of k. This yields m equals 3 and k equals 4. Method 2, as a check, uses root sums and products. For equation 1, the sum of roots is m and the product is m minus 4. For equation 2, the sum of roots is k plus 2 and the product is -k. Since every root in equation 2 is twice a root of equation 1, the sum doubles and the product quadruples. Solving again gives k equals 4 and m equals 3. Final answer: m equals 3 and k equals 4. To visualize the scaling, think of each root r of equation 1 being sent to 2r, a stretch by a factor of 2. Sums double and products quadruple, which is exactly what our equations captured. We solved the problem in two independent ways and confirmed the same result. The key idea is how scaling the roots by a constant factor transforms the sum and the product of the roots, which directly controls the coefficients. In this lesson, we will solve a parameter problem using the inverse roots idea. The task is to find the real numbers a and b such that the roots of the quadratic 2x squared minus the quantity a plus 1 times x plus 1 equal to 0 are the reciprocals of the roots of the quadratic y squared minus by plus the quantity b minus 1 equal to 0. First, the key fact: if r is a root of ax squared plus bx plus c equals 0, then 1 over r is a root of cy squared plus by plus a equals 0. Let us derive that quickly by substituting x equals 1 over y. Watch the algebra. We start with ax squared plus bx plus c equals 0. Replace x by 1 over y, which gives a over y squared plus b over y plus c equals 0. Multiplying both sides by y squared, we get a plus by plus c, y squared equals 0. Reordering the terms yields c, y squared plus b, y plus a equals 0. That confirms the inverse roots property we will use. Apply the rule to our first quadratic. Here, a equals 2, b equals negative the quantity a plus 1, and c equals 1. So the inverse roots must satisfy the equation y squared minus the quantity a plus 1 times y plus 2 equals 0. For the second quadratic to have exactly those inverse roots, its coefficients must be proportional to 1, negative the quantity a plus 1, and 2. Equivalently, we can set up the classic coefficient matching used in many textbooks. Multiply the first equation by b, and the second by a plus 1, then equate coefficients. Equating the corresponding coefficients gives two relations. First, 2b equals the quantity a plus 1 times the quantity b minus 1. And second, b equals a plus 1. Substitute b equals a plus 1 into the first relation. we obtain 2b equals b times the quantity b minus 1. Bring all terms to one side to get b squared minus 3b equals 0, which factors as b times b minus 3 equals 0. So b is 0 or b is 3. Since b equals a plus 1, the two corresponding values are, if b equals 0, then a equals negative 1. If b equals 3, then a equals 2. But we must check which pair actually satisfies the inverse roots condition. Check the pair a equals negative 1 and b equals 0. The inverse polynomial predicted from the first quadratic is y squared plus 2 equals 0, while the second quadratic becomes y squared minus 1 equals 0. These are not proportional, so this pair does not satisfy the requirement. Now check the pair a equals 2 and b equals 3. The inverse polynomial from the first is y squared minus 3, y plus 2. The second quadratic becomes exactly y squared minus 3, y plus 2 as well. Therefore, this pair satisfies the condition perfectly. Final answer, a equals 2 and b equals 3. Thank you for watching. Don't forget to like, subscribe, and hit the bell icon for more math lessons. NENOMATICA, where mathematics meets YouTube excellence.